So today we are going to see construction of the beam. So what is construction of the beam? The name itself has the answer. We are going to prove that the strength of the beam is constant across the length of the beam. That's what we are going to prove. So constant beam is very easy to fabricate and it is used in anchor structures. That is where we need to understand about the behavior of the construction of the beam. So in construction of the beam, the section modulus is keep on varying to the applied moment. That is why we get the constant strength across the length of the beam. Let us see the schematic of the beam, and then we will see how to get the readings from that beam setup, and then finally we will compute the strength using theoretical formula. So let us see one by one. So you can see this is the front view of the beam. You can see the depth is keep on varying. So in order to prove that the strength is constant along the length of the beam, we have taken three sections. Section A has a length of L1 from the free end. The L1 is 460 mm and it has a depth of H1 is 75 mm. And then we have taken a section called B. Again the B is located around 345 mm from the free end, that is L2, and the depth of the B section is H2, that is 65 mm. And also we have taken one more section called C, section C. Again it has a length of L3 from the free end, which is nothing but 230 mm, and it has a height of H3, which is nothing but 55 mm. So now we have defined the portion of section A, B and C. So now to determine the strain, we are using strain gauges at the top and bottom of the beam. So section A we have two strain gauges, section B we have two strain gauges, and section A two strain gauges. So now we are going to apply the load and we are going to compute the strain from the strain gauges. Let us go to the tabulation. So for seal number 1, I am going to apply a weight of 2 kg. For the 2 kg, I get a strain of 19 microstrain. So the micro stands for 10 power minus 6. So this is the strain we are going to read from the strain gauge indicator. So from section A, I get a strain of 20 microstrain for the period of 2 kg. And then I can measure the strain at section B. Again using the same strain gauge indicator, it shows our 20 microstrain. So like that, for the given set of loading, we will measure the strains at section A, B and C. So now we have got the strains due to the applied load at section A, B and C. Now we need to compute the strength of the beam. How to compute? So as the applied load is within the elastic limit, so we can apply the Hooke's law. So here you can see, so from Hooke's law, we can get the stress data or the strength data. So we know the Young's modulus of aluminum is 70 gigapascal. So it is known value, and we know the strain acting at the section A, that is epsilon A. So just multiply the Young's modulus and strain, you get the strength at the section A. So when I plug in the data, I will be getting around 2.5 Newton per meter square as the strength. So here if you see, I am multiplying with the 2. The reason is we use a half bridge circuit. That is why we need to multiply by 2. So here also I have given the strain gauge spec. It has a resistance of around 50 ohms and it is a gauge factor of 2. So this we will discuss later about the strain gauge. We will have a separate session. As of now, just note down the details of the strain gauge which we are using in this experiment. So similarly, you use the strain at B and compute the sigma B, and use the strain at C and compute the sigma C. So this way you get the strength as 2.5, 2.6 like that. So we have proved that the strength is constant along the length of the beam. So now we have computed the strength experimentally. Now we will see how to compute the strength theoretically. So let us come to the theoretical section. We are going to use the very famous theory of bending formula, that is m by I is equal to sigma by y equal to E by R. From this I am going to take m by I is equal to sigma by y. So here I have given the formula. So to compute the stress, we need to know the applied moment that is M. We need to know the distance from the axis to the area of interest, and then we need to know the section property, that is moment of inertia. So now we are going to introduce a new term called section modulus. So the section modulus is nothing but it is the ratio of moment of inertia to the distance from the axis. So for our section, the section modulus keep on varying, it's not constant. If you see here, I equal to y, where y is nothing but d by 2. So d by 2 is nothing but this is the portion, the place where I will be getting maximum bending stress. So here we have h1 by 2, here we have h2 by 2, here we have h3 by 2. So what we observe from here, the depth is keep on varying. As the depth is varying, we get the variation in the section modulus. So here I have given here. So instead of, so here the section modulus of a beam is nothing but the moment of inertia to the distance from the axis, that is d by 2. So we get Vd square by 6. So now what we do, now we know all the values. Now we are going to plug in all the data. So now what is the formula? My by I, right? So what is M? How to get the moment, bending moment, upright bending moment. So I am going to compute the stress at section A using theoretical formula. So I am applying a load of W. So what is moment? W into L1 will be the upright moment at section A. Similarly, W into L2 is the upright moment at section B. Similarly, W into L3 will be the upright moment at section C. So let us go one by one. First, I am focusing on the section A. I need to compute the strength at section A. So for this upright moment is W into L1. So here I have given. So as we are applying the load in kg, we need to in Newton. That's why I am multiplying with 9.81. Divide by. So again, already we know M by Z. So the Z is nothing but I by Y. So here I have given the formula. So V is the width of the beam. And at section A, we have a depth of H1. You can see here. So apply the H1 value, which is 75 mm, divided by 6. So if you plug in all the data, you get the strength will be around 2.6 Newton per millimeter square. So this way, we can prove that the strength of the beam is constant at all the sections along the length of the beam. So we have done it for A. Similarly, we will do it for section B and section C. Similarly, we will increase the load. So now we have done it for 2 kg. So we can do it for second iteration. Say you can apply 4 kg and you can compute the strains and the stresses. And finally, you can compare the stresses with the experimental value and the theoretical value. So this way, we can prove that the strength is constant along the length of the beam, both theoretically and experimentally.
We have an experimental setup for constant strength beam. This is a cantilever beam fixed at one end. This beam is of 460 mm length and 4 mm thickness. The depth is varying from the root to the tip. In the tip we have a weight hanger where we apply loads. For the applied load, we have strain on the beam. We have multiple strain indicators on the beam. So we have a location 1, 2 and 3. So corresponding wires have been connected to the digital display or the digital indicator where you have your display. Here you can see the strain values. You have channel selector for selecting which strain gauge you want to take data from. Then we have the bridge selector. We have quarter bridge, half bridge and full bridge. Here we are using half bridge for all the strain gauges. Then we have coarse refining and fine refining. So you can set 0 before starting the experiments with that. So once you apply load, you have corresponding strains. You can measure that and you can tabulate it. We will go ahead with loading. Unloading. assembling the setup. First place the weight hanger the tip of the beam, then switch on the experimental setup, choose the selector for bridge, and then choose the coarse one for refining the values. Once the setup is ready, you can go ahead, load and do the experiments. Dismantling, remove the hook, switch off the experimental setup.